Have you ever wondered what a creaky old door, a set of screeching car brakes, and a beautifully played violin could possibly have in common? Well, it turns out they're all powered by the exact same, kind of hidden physical phenomenon. So today, we're going to pull back the curtain on the science of why things stick, slip, and make all sorts of sounds.
Right? I mean, you've got the super jarring sound of brakes, the spooky creak of a door, and then this perfect, beautiful note coming from a violin. One is noise, one is music, but believe it or not, they are all born from the exact same physical principle.
And the answer is something called stick-slip. It's this really rapid, jerky motion that takes stored-up energy and just blasts it out as vibrations. And those vibrations are what we hear as sound, whether it's an annoying squeak or a perfect melody. So let's break down how this actually works.
Okay, to really get stick-slip, we have to talk about the main character in this whole story, friction. But it's not just one simple force. It's really this constant battle between two different types of friction, the one that keeps things from moving at all, and the one that kicks in once things are already in motion.
So here's the official idea. Stick-slip is that jerky, jittering motion you get when two surfaces try to slide past each other. And the key, the entire reason it happens, is the difference between the force you need to start something moving and the force you need to keep it moving. That gap right there, that's everything.
And this graph basically tells the whole story. The up and down axis is the force being applied, and it's moving through time from left to right. Now see that jagged, sawtooth pattern? That is the visual signature of stick-slip in action. Every single one of those peaks and valleys is one stick and one slip.
So let's meet our two contenders in this friction showdown. First up, you've got static friction. This is the stick. It's that really stubborn force you have to push past just to get something to budge. Then, you've got kinetic friction. That's the slip. It's the smaller force that's pushing back on an object that's already sliding.
And here it is, the one fundamental rule that makes this whole thing happen. It almost always takes more force to start an object moving than it does to keep it moving. Static friction is stronger than kinetic friction. This one little fact is the engine that drives every single squeak, judder, and screech you hear.
In fact, that initial peak resistance, that moment of maximum stickiness, has its own cool slang term, stiction, which is just a mashup of static and friction. It's that absolute highest point of force that the surfaces can handle before they finally break free and start to slip.
So let's trace one of those little sawtooths. During the stick phase, you're pushing, you're applying force, but nothing's moving. Instead, the whole system is flexing and storing that energy, kind of like you're compressing a spring. Then once you finally push hard enough to beat that stiction, bam! You hit the slip phase. The object suddenly lurches forward, releasing all that stored energy because the resisting force suddenly drops down to that lower kinetic friction. Then it grabs, it sticks again, and the whole cycle repeats over and over, super fast.
Okay, so that explains the cycle. But it kind of begs the question, right? Why is it so much harder to start something moving than to keep it moving? Well, to answer that, we have to zoom in, way, way in, down to the microscopic level.
So even surfaces that feel perfectly smooth to us are actually, on a microscopic scale, really rough and jagged. They're covered in these tiny little peaks and valleys called asperities. And during that stick phase, these little peaks interlock, kind of like the bristles of two hairbrushes getting snagged on each other. Not only that, but at the points where they touch, atoms can actually form these tiny, weak bonds, almost like microscopic weld joints. Throw in a little electrostatic charge, and you've got this incredibly strong combination of forces that are just locking everything in place.
So that slip isn't a nice, smooth slide at all. It's actually the violent, sudden breaking of all of those microscopic interlocks and atomic bonds all at once. And that super rapid release of energy creates a vibration that travels through the air, hits our ears, and we hear it as a screech or squeak.
So understanding the problem is one thing, but if you're an engineer, you've got to fix it, right? So let's take a look at how they tackle this and get rid of all those unwanted vibrations.
You know, the goal for engineers is actually pretty beautiful and simple. If the whole problem is caused by static friction being bigger than kinetic friction, well, the solution is to make them as close to equal as you possibly can. If you can close that gap, you get rid of that sudden drop in resistance, and that sawtooth pattern on our graph just flattens out into a nice smooth line.
And the number one, most common way to do this is, you guessed it,
Lubrication. You just introduce a fluid, like oil or grease, between the two surfaces. It creates this super thin film that physically keeps those little microscopic peaks from ever interlocking or forming those sticky bonds in the first place.
But of course, not all lubricants are created equal. It's all about trade-offs. You've got vegetable oils that can break down when they get too hot. Animal fats, which are actually great for extreme pressure. Mineral oils. Their thickness changes a lot with temperature. And then you have the fancy synthetic oils, which are super stable and high performance, but yeah, they're going to cost you. So picking the right one is a huge part of the engineering.
But what about when you can't just squirt some grease on something? Think about your car's brakes. You need friction there. In those cases, engineers have to get a lot more clever and actually design the system itself to be resistant to these vibrations. And this is how they model the problem. They can simplify a really complex system down to just these three basic parts: a mass, which is the object, a spring, which represents the system's stiffness or flexibility, and a damper, which is basically like a shock absorber. And you can see on the right, the graphs show what happens. Yep, there's our old friend, that jerky stick-slip motion.
Now don't worry, we're not going to do the math here, but this equation is an incredibly powerful tool for engineers. It's a mathematical model that describes exactly how that mass, stiffness, and damping are all going to interact. It lets them play with the values and predict and control the vibrations before they even have to build a single physical part. It's pretty amazing.
So, out of all those different knobs they can turn in that equation, what's the key to making a system quiet? Well, it turns out the most important thing is damping. Damping is just any effect in the system that makes it lose energy. So by increasing the damping, you're basically creating a place for the energy from that slip to go, so it just dissipates instead of causing a vibration.
And here's what that looks like in the real world. This graph shows a system with a lot of damping. You see how the vibration starts, but instead of continuing in that endless sawtooth pattern, it just dies out really quickly. That is the signature of a well-damped, quiet, stable system. The energy gets absorbed and the motion becomes nice and smooth.
All right, so let's just sum it all up. The big takeaways are that annoying squeak you hear is just a super fast cycle of sticking and slipping. It's all caused by one simple fact. Static friction is stronger than kinetic friction. And the solutions are either to use lubrication to make those two forces more equal, or to add damping to the system to just absorb all that vibrational energy.
So the next time you hear a shoe squeak on a basketball court or the groan of a heavy door, you'll know exactly what's happening on that invisible, microscopic level. You'll know it's a tiny war between two types of friction. So the question is, now that you know the science, what are you going to hear differently in the world around you?